these work? All right. Hello, everyone. This is the first seminar meeting. Yeah. So I guess before we kind of get into the actual meeting, I want to talk about what this kind of meeting is. This is sort of different from like a regular SIGPwny meeting that you might have gone to. In a regular meeting, we teach like some security topic, but we usually focus on like the kind of basic standard stuff, right? Like if we teach phone, like we are teaching like a regular shell code and like direct to win and all the standard techniques. Same goes for web and stuff like that. And all of that stuff is obviously very important to know because like you need to know the basics before you get to doing more advanced stuff. But the point of this kind of meeting is to kind of introduce you to some of the latest cutting edge work in security. And the goal is not that you come out of this understanding every single detail perfectly about what you're talking about. The goal is that kind of you get a sense of like what are the problems that are being looked at in security today, and kind of what are the types of solutions that people are working on. And I guess the other way in which this differs from a regular SIGPwny meeting is that I want to make this a lot less like a lecture and more discussion. Like your thoughts on this stuff are probably as important as what I'm going to say. So yeah, with that, I guess before we get into it, any kind of questions about like you have no idea what this kind of meeting means, or you're like totally lost or something? Yes.
So do you have like a pool of like readings that you're looking to pull from, or?
Yeah, that's a good point. It exists like in my head. And I guess also I should say this first meeting I'm presenting, but the hope is that in the future some of you will present something. And you don't have to be an expert in what you're presenting to be able to present it. Like part of the fun is that you actually learn something as you're presenting. So if you're interested in doing a meeting like this at some point on anything you're interested in, feel free to come talk to me or talk to Roman or somebody else. And even if you're not sure what you want to present on, you have some general idea of like I want to do something in this area, that is also fine. We will help you find something. So yeah, okay, so today's topic is this paper called FUZZWARE. I selected this because it's like something that you'll notice sometimes with a lot of like academic papers is that they sound great when you read them, and then you try to either the code is completely missing, so it's very hard for somebody else to actually use those ideas without re-implementing them, or their code or their tools exist but are very hard to use. Maybe they don't necessarily work as advertised on tests that they did not consider or stuff like that. But this paper is kind of a very high quality paper in the sense that the actual tool is being used now as like a standard thing by a lot of people. I have used it a little bit. Other people have used it. I think this also won an award for like a distinguished artifact, or artifact means like the actual code. So this is the sort of thing that if you find this interesting, you can actually download their code and play with it. Okay, so what is this? There's like a lot of fancy words here in the paper title. Don't be intimidated by those. This is the title of the paper. These are the authors. There's a few people from UC Santa Barbara, that is Shellfish, if you have heard of them. And then there's some people from University of Germany. You can, so the slides are up now, right?
Though, let's go that for a second.
Okay. So if you guys have like a laptop, you can just look up this paper name, and you can actually find this online. It's open access. You can download the PDF if you want to take a look at it. guys, before we get into what this means, has anybody heard of this? If you have, I would like to know your thoughts on it. Has anybody heard of like any of the words in the title of the paper? Yes.
Well, I mean, MMIO, I assume means memory management input output.
That's close. Yeah, it's memory map input output.
And then fuzzing obviously is just you permute a string input a whole bunch of different ways and provide it.
Exactly. So it's like kind of a way of doing randomized testing. Has anybody heard of firmware fuzzing? Yes.
Yeah, it's like you have a firmware embedded system and you're running tests on the inputs of that firmware device for reordering stuff.
Yeah. And I guess we'll see soon that fuzzing firmware is actually a lot harder and kind of a different kind of problem than fuzzing a regular piece of software. Okay, so is anyone having trouble finding the paper if you try to look for it and you can find it?
The sites are live on.
Okay. So yes, you can also get the link from the slides. So yes, before, since like I'm not expecting you guys to be familiar with everything going on here, I want to talk about some background before we actually get into what this paper does. So what is fuzzing, right? So fuzzing is a kind of randomized software testing. What is random testing? Random testing is where you have a piece of software and you just give it random inputs in the hope that it will crash or it will break. This is useful, it works sometimes, but it's not always very good because like just by doing like it's kind of almost dumb in some sense, right? It does not have any intelligent way of selecting inputs. It just hopes that one of the test cases that it randomly picks causes the software to break. So fuzzing is kind of an improvement on this. It's a kind of random testing that optimizes code coverage. So code coverage meaning like, do you go down more paths in the code? Do you reach more of the code with your test cases? And kind of the hope is that, let's say there is a bug in some part of the software somewhere, if you optimize for coverage, if you try to hit as much of the code as possible as you're testing it, you will eventually hit that bug at some point. And when you hit that bug, the software will crash or it will do something that breaks it. To do this, what you need? Well, you need, of course, some way of sending input to the software, but then you also want to know how should I select my test cases so that I actually maximize coverage. And the way that usually fuzzers do this is that when they send the test case to the piece of software, they will get some information about what kind of areas of the code it get from the software. And one way of doing this is that if you have the source code of the software, you compile it with kind of these, it's called instrumentation, where it's like sort of some tracking of coverage that's put in the compiled software. If you don't have the source code, you can still do this with like some other techniques. Once the fuzzer has gotten some sense of what the coverage is, let's say the fuzzer takes some random piece of input, it sends it to the software, software tells it it went through all of these branches. Now the fuzzer will try to select an input that will go through a different set of branches. And the fuzzer will try to prioritize inputs that lead to more coverage. And it will take those inputs and try to mutate and change them in random ways. This has been an extremely successful technique. Like, I'm sure like hundreds of CVs have been found, probably even more. And even today, this is like used by like, a lot of security researchers. If you want some example, like if you want to play with fuzzers yourself, AFL is one of the famous tools that you can try out. WebFuzzer is another one based on LLVM. And like the kind of canonically, the kinds of inputs that this kind of stuff is the best for is like where a program takes a large amount of kind of raw input and then tries to process it in some way. So that's the sort of thing where a fuzzer can actually, it has more leeway in giving things. So any questions? About like what is fuzzing, why is it useful? Okay. So this paper that we're going to talk about today is about embedded systems. It's about fuzzing embedded system firmware. So what is an embedded system? Does anybody want to give me a definition for an embedded system? Okay, an example. Yes.
I mean, I have one attached to me, so insulin pump.
Insulin pump. Yes, that is an embedded system. Yeah.
Like a smart, like a smart assistant.
Sure. Yeah. So like smart devices of any kind. So like actually there is no kind of good perfect definition of embedded systems. Usually they are small, they are specialized for like one particular task as opposed to like a PC that can do everything. Usually they are resource constrained in some way. Like the CPU, like the microcontroller or CPU on an embedded system is a lot less powerful than your like Intel i7 or what is on your PC. And kind of most importantly for us, embedded systems are usually safety critical, meaning that if an embedded system breaks, it's really bad, like an insulin pump, right? If your insulin pump breaks, like your life is in danger at that point. If some system in a car breaks, the lives of the people in the car are in danger. Same goes for an airplane or something like that. Or maybe like you have a smart thermostat or something that for some reason has a bug and sets the temperature in your house to like 30 degrees, right? That's not good. And then you have, of course, industrial systems. So like control systems in factories and stuff like that. I mean, the moral of the story is that because these systems are so safety critical, it's even more important that they be as secure and safe as possible. And that's kind of some of the motivation for doing this work. The third piece of background that I want to talk about is this thing called symbolic execution. Has anyone heard of symbolic execution?
Where you, instead of actually executing the code, you just kind of, like, interpret it at a high level to see where the code will flow.
Yeah.
Yeah.
Right. So normally, like let's say you have a function that adds two numbers, right? It takes two arguments and it returns the sum. Normally, you're going to be executing this function with concrete arguments, so with like actual numbers as the arguments, maybe like 5 and 6, and you get 11. With symbolic execution, the symbolic executor, the symbolic like analysis tool, executes your function with symbolic arguments. So by symbolic, something like a mathematical symbol. Instead of getting a concrete number as the output, you get like a mathematical expression as the output. So like your output might literally be A plus B. One kind of interesting thing here is what happens if you encounter a branch, like an if statement. You have to consider all possible branches in that case, because you don't know what the actual values of your variables are. So like if the function does one thing, if like A is positive and one thing is if A is negative, you will get essentially two states. And in each state, you will have a different set of symbolic values for things. Questions? Yes.
So you're saying like turn a function into like a math function?
Exactly. So it's like you take a piece of code, maybe a function or like just assembly or whatever, and at the end of it, you get a mathematical description of what it's doing. And it's a very powerful idea because you can do like more analysis with this mathematical description. Yes.
So are there any like known hard and fast limitations? I know path explosion is a general problem, but I know like for programs,
Yeah.
maybe a mathematical representation, you need like a context or like something like that to verify to the constraint. Are there things that are going to cause this index to really like choke and die that you found practically, or does it just kind of generally work?
Right. So in my experience, like path explosion is the biggest issue. So this is where you have, so like every branch that you get essentially exponentially increases the number of states that you have, right? So if you have 10 branches, each splits into two parts, you're going to have 2 to the 10 states. And now imagine you have branches in a loop or something. Like your states are going to blow up to the point that the program's memory can't fit them anymore. That is probably the biggest issue. There's also problems that you get sometimes when symbolic expressions become too complicated. So like, let's say you have like 500 variables in one symbolic expression and you're trying to manipulate that the computer, it just gets very slow. In general, like this is a technique that in many cases sounds great in theory until you actually try it because of all of these practical issues. So we will see that in this paper, they actually use it in a very constrained, like simplified situation to make it actually work. If you want to try doing symbolic execution yourself, there is a tool called Anger, ANGR, Python-based tool, very easy to use. You can like, look at their GitHub or docs for more information. Okay, so now let's actually get to what this paper is trying to do. They're trying to fuzz firmware, right? When you fuzz a piece of software, like you have like a classic example, like an XML parsing library. It takes a XML document text and it produces like the parsed version of that, maybe like some tree structure or something. In that case, it's kind of pretty straightforward how you would go about fuzzing that. You have a very clear notion of input, which is the actual text that's going into the document. You have a very clear notion of what it means for the software to break. Maybe it like crashes a segmentation fault or something. And you have a very clear idea of what coverage means because you can actually, if you have the source code, you can compile it to track coverage. The problem is that for an embedded system, none of this really holds true. So the first issue is how do we deal with, I mean, to be able to fuzz the software, you have to actually run it. And even that is not easy for a piece of embedded firmware. When you're running like some regular program on your machine, your operating system is doing so much work for you that actually allows the program to run. On an embedded device, usually the firmware is running directly on the hardware. So it's very hard to actually run it outside of the hardware. You need to be able to run it outside of the hardware to do any kind of analysis on it. So to run it outside of the hardware, there is something you call like emulation or rehosting. If anybody has used FUZZWARE here, that is an emulator. It lets you run software meant for like one platform on a different platform. With embedded firmware, the main issue is that you have to not only model like the actual CPU, which is doable since there is a small number of possible CPUs, but you have to model all of the rest of the hardware. So let's say your embedded system takes input from a touchscreen. That touchscreen internally is going to be like some kind of peripheral interface mapped to some region of memory. That's what you call memory mapped I/O, where your peripheral interfaces are mapped to memory. You have no idea usually when you're fuzzing a system what exactly all of that looks like, and to get an accurate enough idea of that takes a lot of time and a lot of effort. And you have to do this usually again and again for every device that you're trying to analyze, because these things differ between devices. So that makes it hard to even run the firmware. So that's like a big issue. Another issue is that like what is the notion of input to the firmware, right? Like what do we call input for? If you have a user program, there's like standard in or takes command line arguments or something. That's a very clear notion of input. But for an embedded firmware, what would you even consider to be input? Does anybody have any ideas? What is input to an embedded device? Yes.
Sorry.
Okay.
I mean, I would assume if it's IO, then you would just like manually set memory locations that the firmware reads.
Yeah, exactly. So the notion of input is the actual MMIO itself, because like let's say the firmware reads data from some serial interface like USB or something like that. Internally, all of that is MMIO accesses. So as far as the firmware is concerned, at the lowest level, it's accessing MMIO. So all of its input is coming from MMIO. Like there's one small exception called direct memory access, but we don't have to worry about that. But in general, a lot of the firmware's input is coming from MMIO. And also it is MMIO that makes firmware hard to emulate. So there's kind of two problems, both related to one issue, which is how to deal with MMIO. Like concretely, let's say a piece of firmware is executing, it accesses some MMIO value. Maybe it accesses like what is the byte that was sent from a touchscreen device. What value should we give it at that point? Right? We don't know exactly how that interface works. So that makes it hard to emulate. Also, that is the thing that we want to control as we're fuzzing. The solution, well, before I get to the solution, does anybody have an idea for a solution?
I mean, I don't know if this is feasible, could you reverse engineer it, check all the branches, get the value of each branch, and make that a set space of things you can enter in as values?
Okay, so yes, good point. You can reverse engineer the firmware. We want to do this with no reverse engineering.
Okay, so you can't do that automatically either?
Well, you can, in some sense, which is what the point of this paper actually is.
Oh, okay.
But yeah, so to be clear, you do not want to waste months and months reverse engineering firmware. Like I have reverse engineered firmware, it takes a very long time for even one piece of firmware. You want to test like 25 pieces of firmware, right? So you want to do this as automatically as you possibly can. Maybe you like reverse engineer only a little bit just to figure out like at least what CPU architecture is this one, like the basics. Yes.
Okay, so like reading an overview of the abstract.
Yeah.
It specifically points out that it's a software-only system. Does that have anything to do with uniqueness and what you're asking about?
So what is a software-only system?
Well, FUZZWARE
Sure.
is a software-only system.
Yeah.
So, because I'm not really involved in this space, I kind of want to just know. Would there be a difference in software-only system and do hardware systems of this nature exist?
Yeah. Yeah, good point. So software-only system, I think what they mean is that you do not need the actual hardware that the firmware is supposed to run on to be able to do this analysis. Because you're doing this emulation, you're taking this firmware and running it on a different machine, your PC maybe. I think I may be wrong. I think there is actually work on doing fuzzing involving the hardware. I don't know a lot about it, but I think it exists. It is probably even harder because now you have to like somehow communicate coverage information and stuff from the hardware back to your host computer. Yeah. Okay. So before we move on, like again to summarize the problem that we're trying to solve. Emulating firmware is hard because we don't know how to deal with MMIO accesses. And MMIO accesses are the things that are input to the firmware. So these are the things that we want to put our fuzzer input into. So the solution is, well, a naive solution would be that, okay, you just take all of your fuzzer input, the fuzzer just generates like random bits or bytes, and you just throw that into the MMIO values whenever they're required. Right, so like the firmware asks for 4 bytes of MMIO access, you give it 4 bytes of firmware fuzzer input. Does anybody see any issues with this? So it would at least deal with the problem of like, what do you do when you get an MMIO access? You have some value to give it, but is this actually going to do anything? Is it going to happen?
It seems like the naive solution.
It is the nice solution, but we should think about why this is a bad space. Sometimes a nice solution is a great solution. Yes.
I would assume you would just get trapped in the whatever if statement they use to check that's a valid statement forever.
Precisely. When the fuzzer has no understanding of what an embedded device means, what firmware means, all the fuzzer understands is random bytes. If you take a piece of like 4 random bytes and you give it to the firmware, it's expecting like maybe it's in a while loop waiting for some kind of status to be communicated to it. unless the fuzzer randomly happens to give it that precise value that it's expecting, it's gonna be stuck in the while loop forever. You're not gonna get anywhere. Or like with an if condition, you will, it is gonna be hard for you to explore much. I mean, the point is you're trying to maximize coverage, right? And this is not a great way of maximizing coverage because you're not going to be able to cover as many branches as you want. Okay, does anybody have a solution to this problem? Like it's fine if it's like a bad idea, like that is also not a problem. If you have any idea, any even like a very small optimization maybe.
I mean, reverse engineering is not scope though, right?
Reverse engineering is out of scope.
Yeah.
Like beyond the most basic, like here's the memory map, here's the CPU architecture. That is all you're allowed to do. Yes.
We could read the documentation of the peripherals.
You have no documentation.
No documentation.
So is there any way of making it aware of the output state without knowing the meaning of it? Perhaps get an absolute difference in the function that you're entering and try to go somewhere else?
Do you want to? Sorry, I don't like totally understand what you mean.
Okay, sure. So if you get caught, if you're like, hey, I don't want to look at what the code does, but I can see I'm setting a jump, I'm going to put an error handling death loop. Is there a way to optimize from saying, hey, I've seen this before, let's go somewhere new, right? And just try to mutate it until we end up somewhere new.
Right, yeah, that is really what we are trying to do. We want to go to new places, but then that runs into the issue of like one, how do you detect that you're in an error handling loop? Maybe somehow you can detect that you're in some kind of loop. Sure. Yes.
We use symbolic execution.
Yes, it is symbolic
So
execution.
because we have the mathematical representations of the state of the variables, and we know what branches exist, and we want to go down probably each branch, so we can solve for certain variables.
Yeah. Precisely, yes. So it's kind of like an enhanced version of what Ronan was saying. So let's say you somehow detect that you're in a loop by some means. Now we want to get out of this loop. One approach that you could do is just like try to randomly mutate the input with the hopes that you get out, right? But maybe the loop expects one specific magic value from the MMIO access to get out. And there's like an integer is like 2 to 32 values, right? Like it's almost impossible that just randomly you're going to end up with that value. So we need some more intelligent solution. We want to actually know what values of the MMIO input are meaningful. If you have some kind of while loop, like there's only one meaningful value that might characterize at that point. All other values are yes.
If we only care, or if we're trying to do coverage, right? And
Yeah.
coverage is determined by branch paths, then is it possible to do branch to branch symbolic execution? Or create a symbolic representation from branch to branch? Because you said like the problem with symbolic execution is that once you start branching, it gets terrible.
Right.
So if we create branch to branch, then we'll only have 2 at any given point.
So you stop at the next branch, essentially?
Yeah.
Yeah, right. So that's a very good idea, actually. And this paper actually does have some notion of when to stop symbolic execution. I think it's not quite when you get to the next branch, where I think they have like a list of conditions, one where you exit the current function, one where you I think like all the symbolic values are no longer being used or stuff like that. But no, this is a good idea. Like why don't we stop at the next branch? Yeah, good point. And then I guess you would, when you get to the next branch, you would do that again. Okay, so to kind of formalize what we have been talking about, they call this, they use this term called input overhead. What this basically means is that you read some input, right? And there's some amount of information contained in that raw input. Maybe if it's an int, there's 32 bits of information in that input. But in fact, that input, like all of the information in that input may not be significant. Like this is a figure that I stole from the paper. They read some value from MIO, and then they compare it against A, B, and C. And there's a default case. So, question, how many really meaningful values are there of this input? There's 2 to the 32 possible values, assuming this is a name. But how many of those are actually meaningful values?
5.
5 is close. Which one?
A, B, C special, C default, and else.
Oh, the C special, that's a different tree. The MIO status is a separate.
Okay, I for some reason assumed it was the one register was an off block and status block in the one thing.
I think it's 2 different registers. Well, yeah, anyways, it's like kind of not important. Yes, but there's a small number of meaningful values. Like if we only look at the top level, there's only 4 meaningful values, right? A, B, C, and something else. So the fuzzer does not need to waste time generating a bunch of values that are all going to end up in the default case, most likely. Because just by random chance, the chance that it hits A, B, or C is quite small. Even if the firmware does something like, oh, it only takes the last byte, right? It masks out everything except the last byte, it compares that to A, B, and C. That is slightly better. Now you have only 256 possible values, of which you're comparing against 3. But still, it's very, like, there's a lot of redundancy. And like in a more extreme case, you have that if condition, right? Where only one value is really important. The fuzzer is going to spend a lot of time generating random values that are going to be kind of useless because they will all end up in one branch, probably less. Right? So what we really want to do is when you get an MIO read, you want to figure out what are the important significant values of this MIO read. And the solution is symbolic execution. Does anybody have an idea for, like, let's say you have this specific function, right? How would you, or what would you make symbolic? What variable or what read memory access would you make symbolic? Yes?
Only what's going in the switch statement.
Yeah, so the MIO op value, you're gonna make that a symbolic variable when it gets accessed. Once you have the symbolic variable, now your symbolic state is going to split into 4 parts, depending on the case. And then in each case, something happens, right? And now from these 4 states, each state also keeps track in symbolic execution of the conditions that need to be satisfied to get to that state. So like the A state is going to keep track of the condition that an MIO op is equal to A. And so on for the other state. So now you know in each state what values make it reach that state. And now you can precisely generate those values. Now you know, like, to be able to optimize coverage, I need these 4 values of the variable. And you can do a similar thing for MIO status. Questions? Okay. Yeah, so this is what we were talking about. You use symbolic execution starting at these MIO accesses to figure out the kind of significant, meaningful values. When you do this, and that's like one optimization that they use, which is that you don't want to do this. The symbolic execution is a lot slower than concrete, regular execution. And one of the things that's very important in fuzzing is that it needs to be fast, because ultimately fuzzing is still randomized testing, and you want to be able to test like millions of test cases or a large number of test cases. So it needs to be, like, the faster it is, the more you can do with it usually. So they do like some sort of optimization with like caching and stuff, where if you've already seen this kind of access, maybe you were at this specific point in the code before, and you generated or you analyzed it and you figured out, okay, these are the possible values that you could have. You don't need to do that again. Just use the values from last time. And now once you have these set of meaningful values, now the fuzzer input can be used to actually generate one of these values. So in the previous case, if I go back to the last slide, ordinarily the MMI op, assuming it's like a 32-bit read, would have consumed 32 bits of input from the fuzzer, 32 bits of random data. Instead, how many bits do you need to represent 4 values? Question. Yes, 2 bits, right? So now you only need 2 bits of fuzzer input. And these 2 bits are gonna do a lot more than your 32 bits. Because these 2 bits, like every different choice goes to a different branch. So you get much better code coverage. And I think if you look at the results from the paper, I think it's like 3 or 4 times better coverage compared to some existing solutions. This is a diagram of what their design looks like, again, stolen from their paper. So there is so ISA emulator just means the like CPU emulator. If you use something like the Unicorn engine, that is what this is. So it only emulates the CPU, does not emulate any peripherals, any other hardware. Like think of it as like a very stripped down version of something like Smooth. When this accesses, when you get an MMIO access, so like the top right arrow, it goes and asks the MMIO access model what are the meaningful values, what values do I need to, what are the options that you have for this value. The MMIO access model knows that, and it consumes the appropriate amount of fuzzer input, maybe like if there's 4 values, then 2 bits of fuzzer input, and it provides a value to the firmware. This kind of spins in the loop. I have a question now for you. So I said in the beginning that to do fuzzing, you have to keep track of coverage, right? But we have firmware, we don't have the source code for it. So how do we keep track of coverage? Because the fuzzer still needs to keep track of coverage. So like all of this is an attempt to improve in some sense like the efficiency of the fuzzer, the speed at which it can explore new branches. But the fuzzer still needs coverage feedback from this process to mutate inputs. So what do we do? How like let's say we give a particular input, how do we know what is the coverage? Yes.
Right, this is like a really cursed idea, so bear with me. So I'm not allowed to really read the code, but can we go through it and count the number of relative jumps and use that to create a set of pseudo labels and then see how many of those we get?
Okay, how do you propose counting relative jumps? Like, do you keep
by looking for like, again, a label is going to be like, hey, jump this fixed offset. Look for a thing where you have, ideally you have on anything, but for like short jumps, I would say, look for anything where 2 things jump to the same location, count that as a state.
Sure.
Find all of those, because we can do that in like O(n) time and size quite quickly, right? And then we have a naive count of the number of labels. It's going to be wrong, but it's at least like a guideline.
So are you suggesting we do this like statically? Just
I would suggest that before you begin fuzzing, you run a pass through of this, count the number of relative jumps that go to these places, and use those like landing sites or potential states.
That's a good point. It's definitely a good idea, but I think one issue with this is that, for one thing, in firmware, like there is no good distinction, including ARM. I know this holds true for ARM, probably for other architectures. They like to mix coded data in the firmware image. So you get
jumping to. Oh,
so like a piece of data may be wrongly interpreted as a jump, right? If you have like static data in the firmware.
I mean, I've seen this before. Yeah, because by the time I've like run like disass on a block of data and seen it give you an instruction set. But if you have that requirement, again, where you're gonna say, hey, we're gonna undershoot and have 2 things jump to the same, like, unless it's some like really ubiquitous sequence of bytes, I don't think that would occur randomly. And this happened on a system like x86, which is like an enormous amount of instructions. So I don't know.
Well, okay, and also like let's say you do this and you keep track of here's all the locations of the jump instructions. You still have to keep track of when those are hit dynamically, right? So like it doesn't eliminate dynamic analysis or instrumentation. Because like I know I have a jump instruction at this address, sure, but like as my code is executing in the fuzzer, I need to know was this actually reached. Yeah.
So what if we do that but like a little bit simpler, where instead of like going through scanning the whole thing, we just say, okay, so let's say we start the code, right? We record the PC, then we go to the first jump instruction, which we can know if an instruction is a jump instruction because we're using an emulator. So we go to the first jump instruction and we say, okay, this block of code from here to here, right? So we can like basically do a highlighter, say, hey, we've highlighted this bit of code, we've covered this.
Sure.
We jump, we've gone to the next like instruction, or like next
Mhm.
section of the firmware.
Yeah.
Now we start the PC, we go down to the next branch, right? We highlight it, we say, okay, here we are. So, and then we can just do like that as a percentage,
So
and then, or like highlight which areas of whatever soft executable we have, and say,
So do you-
cover these.
do you suggest, good idea, do you suggest doing this kind of statically before you actually execute the firmware or as it's executing?
I would assume you would have to do it as it's.
Exactly. And this is more or less what is done. So the like notion of that highlighting that you talked about, I guess technical word for that is a basic block. Basic block is a straight line piece of code. So it's a piece of code, I think, like the exact definition is there's only one way to enter and only one way to exit. There's no branches, no jumping going on inside. And whenever you make a transition from one basic block to another, that counts as like an edge you can think of in a graph. And one measure of coverage is how many of those edges did you pick. So if I jump from the basic block at address A to address B, the edge from A to B would count toward the coverage. And dynamically, as you're executing, as you said, you know where the jumps and branches are. Right? You can see them. This, of course, adds some, like, what is the downside of this, right? Like, it works, and it is what it's done. If you want to, so there's this piece of software called AFL Unicorn, that basically does this. So you can look that up. But then there is a downside to this. Like, why is this not the standard way of doing things? We have to do it for firmware because we don't have source code. But like, why is this not an ideal approach? So fuzzing, you want stuff to be fast because the faster you are, the more test cases that you can run in a given piece of time. So why does this? What's kind of the trade-off over here?
I mean, I could imagine it would be slow because you have to keep track of a lot of things.
Yeah, exactly. It's slow because you have to, like, as code is executing, you have to observe what is going on there, and you can't just let it run as it wants to. So like some optimizations that are sometimes used in emulators to make the stuff faster, you cannot do anymore. But I mean, it's a compromise, right? It's what you need to be able to make this work. If people have different ideas for how to make this work that solve this problem, like I don't have any ideas, but if you do, then that would be interesting. So like the problem is you have code that you don't have source code for. Like there's no inbuilt tracking in the code because like the way usually you would do this is that you would compile it so that you actually add instructions in the code that do this tracking, so it just happens automatically. But you don't have that luxury. But you still want to keep track of coverage.
Isn't doing this sight unseen like a halting problem tier issue, and we're just coming up with cheap hacks to try to make it work?
Well, it's dynamic. You don't want to do this like for all possible inputs in advance. The problem is for a given concrete execution trace, let's say, what was the coverage? How many basic blocks were picked? How many edges were traversed?
I mean, the issue is if you're not looking for the code, right? Like then there's all sorts of weird issues, like like dead code, right? Where it's like in there, but you will literally never hit it.
Yeah.
I don't know.
Yeah, I mean, I don't know either. Like, yeah, it's just like an open question. Yes.
Isn't this something you can just handle in the emulator?
This is
If we're doing a basic block, then you can just add like one specific line to however you're interpreting the jump instruction. And you say, hey, mark this separate field somewhere that the emulator doesn't really know about. You're having something that's processing that field, maybe asynchronously, just help you out.
That is correct. I think that is actually the state of the art way of doing it. Because the way like something like Kimu works is that it like kind of jigs it dynamically translates your the firmware code into the host code or something at a basic block level. I think maybe another thing that you could try, I don't know, maybe this doesn't even work, is if you get to a state that you've seen before, like you don't need to keep executing. So you like cache somehow previous states.
So that'd be you have like a bunch of other variables, right? Like you have like potentially global variables.
Yeah. No, it's
right. So like,
right.
are you defining a state as in the entire program?
Yeah, the state would have to be the entire program state, which is
terrible to store.
Exactly. It is probably even slower than the current approach because
hash map, there would still be
but like you have to hash like
the whole program.
like megabytes of data. So it's maybe it's not a great idea. Okay, so this is all that I have to say about FUZZWARE. Now I want to know what you have to say about it. So I have some questions here. You don't have to like answer any of these or like talk about any of these. Like anything you have to say about this approach or anything about this paper. Like we want to like have some kind of discussion.
There is something. So like you have the hash entire program, but could you do symbolic analysis to see what variables are relevant to that function and then just hash based off of those?
Okay. That's a good idea. So like the extreme case of that would be if you can prove that a function is a pure function, meaning that it does not it does not change any global state. Maybe you can also prove that it doesn't even access any global state. So the only state that it keeps is its arguments. Maybe this function is like some mathematical calculation. It takes a bunch of numbers and does computation. And if you can, with your symbolic execution, prove that this function will never access external memory or never touch external memory, you can do something like that. You can, of course, also analyze, like if you are able to statically analyze what are like the memory dependencies of each function, that would also work. Then, like at a function level, you could do that kind of caching.
So I'd like an algorithms question.
Yes.
Which is like way outside my area of expertise, but I know for chess, right? This is your classic path explosion problem, and because we know things about like the structure of the game of chess, you can do an enormous amount of branching optimization, which is why we have stockfish look out to like depth 21 or something, which is like that naively be insane.
Probably depth 21. Was that only?
Can you go farther now?
I think we're getting like 50.
Okay, last time I checked it was 21, so like 3 years ago. So apparently they've gotten like even better.
You don't have my stockfish on each chest, you have a 45.
My goodness. Okay, so anyways, I was gonna say, obviously there's a lot of the program that we don't know.
Yeah.
But is there anything we can just use about like the structure of how things are computed, right? Just like assembly in general, to start cutting branches or recognizing identical branches to make this algorithmically faster at scale? Or is this like an unsolvable problem?
So I guess we want to think about like what is the goal of doing this? The goal is to maximize coverage. The goal is to create as much of the program, like to explore more branches.
Yeah.
Like the more branches you explore, the better, right? If you have some heuristics that will tell you like, oh, I think a bug is like in this section of code, and you have like some kind of heuristics that can guide you toward that bug, you could possibly do that.
Yeah, I'll just say heuristics for avoiding things that would not look like duplicates, but actually are. Kind of like how you use symbolic execution to refine like the 32 bits down to like 2 bits, right? So like what if you're like hey, branching in a loop and you go like branching and then coming back and branching, coming back? Those are actually the same thing.
Oh sure,
Can you
yeah.
syntax your way out of that, or is that
that you can definitely get out of, and I think that there's already techniques for detecting whether you are stuck in a loop.
Okay.
And you can even do that statically. Like one way, like in the simplest case, if you have, let's say, a while loop that checks while some variable is equal to something spin, your control flow graph or your like graph of program states is going to look like you have some node that checks is this variable equal to this value. If yes, then you loop back to you loop back to the same block. If no, then you get out. Statically, just from looking at this, you can check that there is a cycle here, and the only way to get out of the cycle is to
okay.
Yeah. So I mean, you can. There are static ways to check that you're stuck in an infinite loop.
Okay.
I thought what you meant was like, can we ignore certain branches entirely?
Yeah, I meant like pruning basically. So
Yeah.
Anchor did this like with some settings, they don't know which ones.
Right.
And it was still like.
Yeah, again, I think if you want to do, because like with a chess engine, you're trying to get to a goal state. Like you're searching for one state. And your heuristics tell you that, oh, these branches are not important to look at because the state is not going to be one thing. But
Isn't your goal state having the program counter being symbolically tied to any other variable that's in your input space?
right, okay, so we are not doing symbolic execution here to actually find those cases. Those are being found by the fuzzing.
Okay.
The symbolic execution is strictly limited to the MMIO like input overhead reduction.
Okay.
Yeah, that kind of analysis, yeah, you can definitely, if you have that kind of goal state in mind, then you can do that sort of thing.
Okay.
Here it's kind of like with fuzzing, you're just exploring as much of the program as you can. And the symbolic execution is helping the fuzzer be more efficient.
Okay, for some reason I thought these were both the same technique. I didn't realize they were separated, so.
Well,
Yeah.
so I think the difference here is like, so here they end the symbolic execution very early. They don't like check for, oh, is the PC symbolic or something. They end it when they have figured out all of the information that they need about the MIO access. Yeah. Other questions, discussions? Okay, well, I have a question. Do you think this idea, this input overhead idea, could this also work for non-embedded software, like just regular software? Is this a useful concept, this kind of symbolic execution approach? Yeah. No, but many of you.
Well, I would say sure.
Yeah.
Like, I think the best analogy would just be like network software,
Okay.
right? Because network software, you have the same problem of like,
Yeah.
you don't have defined inputs and outputs.
Uh-huh.
So if you're like scanning over the like network inputs,
Yeah.
you can do the same thing with looking for magic values.
Exactly. Yes. Yeah, I mean, in fact, actually, I don't know if you looked at the paper, but the things that they fuzz were network stacks of embedded systems in this paper, mostly. But yes, yeah, if you have any kinds of magic values in your code, then this is a very good approach. And I think actually there's work on doing this, I forget what's it called. Maybe Driller might be what it is.
Oh, yes, I read this actually.
Yeah, you can look up, there's this paper called Driller from some folks at CMU, I think, that there I think the way, I mean, I haven't actually read their paper in full part. I think what they do is they have a way of detecting if the fuzzer is stuck, if it's not able to make progress. And if it gets into that situation, then they trigger the symbolic analysis to try to get the fuzzer unstuck. So maybe like they look at where are all the paths of the branches that the fuzzer is taking, and can we find inputs that will make it take a different branch? Other ideas on this? Okay. Next question. So the kind of model, the scenario in this paper is that we don't have any source code, right? All we have is a firmware image. We don't have documentation, no source code, like we know nothing about this piece of software. If we had source code, could we do better than what they did here?
No.
No, why not?
There's not any information lost in compilation, except to make it easier to read. You can extract all that state just by reading the assembly.
Okay.
And this is how you get taught to do it, like in certain like when I was going through the exploit dev training, you don't use the decompiler, like you don't read the C, that's for like cheating. You just look at the states as assembly branches. So you're just looking at the number of jumps.
Okay.
So I would say that for the purpose of like what this is doing, especially, there's absolutely zero loss of information. You have
Okay.
everything you need on the computer.
That is an idea. Does anyone yes?
You also make the claim that like, for fuzzing specifically, speed is one of the more
Yeah.
important factors. Because if you're going over a bunch of inputs, you could end up having, even with like perfect information, it takes forever, that it's not a useful fuzzing method. So like having source code can make fuzzing faster, which makes it more useful.
So how would you make it like, what would you change that would make it faster?
I mean, given code maps more directly to like symbols, let's say, like different mathematical operations than just normal assembly.
Sure.
So if you know the source code, then you can symbolically execute that instead.
Right.
That'll be a lot faster because you don't have to go through every single assembly instruction and get from there to a symbol.
Would it necessarily be faster though? Like, in my mind, like, these things seem like equivalent.
Well, let's say in just the most common example, right? So go back to the switch case.
Yeah.
But like a switch case in assembly is like a whole bunch of if-else statements, right?
Yeah, but like, what model of computation can symbolically execute C source code?
There are symbolic executors for C, like source.
Really?
Yes.
Wow, okay, I've never heard of this. Like, what's it called?
Okay. There is this thing called FrameC, that may be wrong. So that, I think it does symbolic execution. I may be wrong. I'm pretty sure it does symbolic execution.
Okay.
There's symbolic executors for Rust also, actually.
What the hell?
I think
I
it's called like
know it's
Can, like K-N-I, Can.
Okay. You go look at that. That's crazy.
I have never used any of this, so I don't actually know if it's faster. Maybe it is.
I mean, I would assume so, because like this switch case, instead of going through the assembly and trying to read values or
Yeah.
start computing magic values,
Uh-huh.
you can just say, okay, in the source code, you see a case, okay, case means match value. Let's look, what's the match value? There we go.
Yeah.
And then when we have all these functions which show us, okay, this function is a region of code, and we can take
Yeah.
out some of that assembly.
Certainly your static analysis gets a lot more powerful when you do this. Yeah, I guess you can do like, you see an MIO access, you know there's a switch construct, so you can like ask, okay, what's the thing? Yeah. Another thing you can do is you can also compile with instrumentation. That can help. Another thing actually that you can do if you have source code is you can, so this is slightly out of scope for this paper, but there is this other tool called Hallucinator. Manny, do you want to, what is Hallucinator?
So it's actually kind of worked on by Professor looking at UAC as well. But it's basically, I actually don't know. The thing is, like, I haven't worked with Hallucinator.
Sure.
I only worked here in research discussions.
Okay.
But it is sort of like an emulator.
Yeah, it's a way to emulate firmware. So what they do is they abstract the hardware at the level of this thing called the hardware abstraction layer. So the hardware abstraction layer is like, or hardware abstraction library, whatever it's called. It's this library layer, whatever, that has a bunch of functions that give you access to the hardware. So usually when like a programmer is writing embedded software, they are not accessing low-level registers manually. They are accessing the hardware through these functions that provide some abstractions. And these abstractions usually are the same across different devices. The underlying hardware may be different. So if we can come up with a model of a peripheral and plug that in place of the HAL function. So instead of the HAL function doing MMIO accesses, the HAL function just hooks out to your model of a peripheral device. That lets you emulate firmware kind of more easily. So like a concrete example, like let's say you're doing like a UART read byte. And the MMIO, I think basically what it's going to do is it will pull some status register, then it will read some data register, something like that. But you don't need to know all of this if you know that, okay, this is the function that actually does this, right? This function can just say, okay, I need to read a byte. So I'm going to go to my model of how this device works, and I'm going to just give it a byte from that. No need to worry about the lattices. So you can do that kind of thing. It is also slow because now you have all of this communication going on between your MMI, like your HAL library and your models. Maybe somehow if you like, I don't know if anybody has done this, if you maybe somehow compile the models into the code, make it faster. Next question. Can we do more than fuzzing with this idea? So in this paper, they use this input overhead stuff and all of that kind of stuff to do fuzzing. can some of these ideas be used to do something else? So I mean, one of the big problems also in firmware analysis is accurate emulation of firmware. So this is not going to get you accurate emulation, by the way. Like, if you want, like, if you have a insulin pump, let's say, right, and you want to actually run it like realistically on your machine, this is not going to do that because the values it's given to the MMIO are like they may not be physically meaningful in any way. They are only optimized to explore as much of the code space. Maybe you have like a smart device or whatever. Like you will not, you don't know how the screen looks like. So can we do more than just fuzzing? Ideas? No? And I don't know. Like I don't know the answers to any of these questions either, which is why I couldn't do. Okay, maybe we'll come back to this. Do you see any issues with this approach or any ways to make it better? Like, are there cases where you think this may, like a lot of the stuff is heuristics and in general, at least from what I've seen, a lot of the research and kind of this firmware analysis space, there's a lot of like just heuristics that you develop based on your experience. Yeah.
I mean, I think they made too few allowances
Okay.
in this paper. Like they're saying, oh, we don't know anything. All we have is assembly and architecture.
Sure.
Right? Like I don't think that's realistic unless you're doing some like hardcore, oh, we're hacking some drone or something, right? Where we literally cannot know anything. But I would think most people, or like in real life, if you were doing this, you have access to the company's software or the company's documentation or the software documentation.
Yeah.
So you will know more, and I think you could use those to develop the heuristics that you need to optimize.
Right, so I guess you're saying that like their threat model is not very realistic.
Yeah.
Yeah, I guess that's a fair point. I think their kind of model that you're looking at is you are an attacker who's trying to break an embedded system developed by somebody who's hostile to you. So they will not give you anything.
The firmware includes you have access to the system, right?
No, you won't.
Like physically own a
Maybe so, maybe you got the firmware by some other means, you pulled it up. Yeah, but the people who develop this system, they don't like it. So they are not gonna give you anything. Maybe this is like a super secret system that nobody knows how it works.
I had the same kind of idea. I feel like there's almost always going to be something to be doing at least one pass of static analysis.
Yeah, no, I mean, of course there's, yeah.
Right, I don't know if there's a way to really, nicely link that up with the dynamic component, because the dynamic component is really pretty like well established on its own for things like finding branches and stuff.
Yeah.
But you have a lot, like you have a compiled program, you have a lot of information.
Oh, yeah.
All the information you would ever need.
Yes.
To know if it's exploitable. So not really touching that outside of runtime feels kind of weird to me, but I don't know a concrete way of like using it to speed things up.
Yeah, fair enough. I mean, I guess like maybe all of the information that you need is in the code, yes, right? But it may not be usable very easily. Like think about, if you like obfuscate a binary, all of the information is still in the code. Like it did not destroy any information, right? But it is now infinitely harder to analyze without like decompile it on obfuscation.
This is really cursed, but technically, if you do some Boolean algebra, is it not possible to like just totally recover it? Because if you think about what an obfuscator is and how it works, right? You could, it's not symbolic execution, but you could do static analysis Boolean algebra to make it more readable and much shorter.
No, you can do that kind of analysis. The problem is it actually feasible with the scale of the problem? Like, I mean, we should remember, of course, that all of this analysis, symbolic execution, is based on some very iffy, like theoretical base. So SAT solving is NP-complete. SMT, of course, also is NP-complete. The general problem of like a lot of the things that we try to do, like are two programs doing the same thing? Can we get a mathematical description of the program? All of these are in general undecidable due to a halting problem and various other issues. So like the hope with all of these is that the practical cases just happen to work nicely. In many cases they do. But if you try to do like a full symbolic execution of a firmware binary, it's not going to happen. Maybe not even decidable. Yeah. Any improvement? Yes.
Sure. But this, does the paper talk about like interrupt base?
Yes, good point. Very good point. Yes, this actually I did not forgot to talk about. Yeah.
So I can quickly like, so by interrupt base I mean like suppose instead of like busy waiting for your input, you wait for your peripheral to when it gets a byte, then it raises an interrupt and
Right.
handle that.
Yeah, that's a good point. So their solution to this, which is in one sense kind of stupid, but also in another sense actually reasonable, is that at some regular intervals they raise all interrupts that are enabled. So it's definitely it's certainly not realistic, right? But if you think about it, like fuzzing is just trying to explore more of the program. And by raising all the interrupts, you explore more of the program. You run all the interrupt handlers. So yeah, that's what they do.
That's interesting.
I mean, this is, I think, actually, I've seen this kind of stuff elsewhere, like how the way you handle interrupts is just by throwing, like, spamming your interrupts at your device randomly. I think the rationale for this is that usually you would design a device without making any assumptions about, like, I will only get interrupts at this time, I will like, only get this combination of interrupts. Usually, like, it would be fine to get. Like, the device would not blow up if this actually happens to it. It's probably not going to ever happen to it, but yeah.
So wait, maybe I'm like misunderstanding this fundamentally. It seems like kind of a missed opportunity in the context of the main paper. Can't you syntax as to which interrupts are relevant and when, just like they did in Maya? Or not?
Well, I mean, interrupts are kind of like, they happen due to external events, right? So like, how can you?
Like, for example, a Control-Alt-Delete,
Yeah,
which is 3 interrupts, works very differently than ABC.
sure.
That's what I'm saying. The space on 3 keystrokes is, yeah, sure, not going to have any like event-based thing. Those are 2 very different operations. So in the same way we were talking about reducing the input space for MIO, would it be possible to do this for interrupt? It's just not even feasible. Or
I mean,
how it works.
I guess like, okay, so let's say you have a device that's reading UART, suppose, and the UART produces an interrupt when it gets a byte. Like, how would you know or be able to predict when you will get those? Like, they could happen at completely arbitrary times, right?
Yeah.
And like, maybe like based on domain-specific knowledge of what this device does, you can have some idea of like, if I get this interrupt, maybe it will be followed by this interrupt shortly after.
I mean, could you identify like side effects from the interrupt function and then symbolize all of them?
What would you gain from doing that?
By figuring out what combination of interrupts are meaningful.
Well, I guess, what does meaningful mean?
Well, this kind of domain specific, but like I said before, if you have the control delete, this is going to be taking you somewhere else, which is functionality. So kind of like I said before.
Oh, I see what
taking
you mean.
somewhere
Yeah,
else,
yeah,
right? Does that make sense?
Yeah, that makes sense. That's a good point. I think I guess the idea is that if you just do all the interrupts, then you will cover every possible case, right?
Not really. If I go A, B, C, D, E, F, G, right?
No, but like those are all,
Yeah.
but those are all like different, like they are all the same type, and they're all keyboard interrupts, right?
Yeah.
Like here they are, like maybe there's a UART, maybe there's like a touch screen device, there's like a bunch of peripherals. They will raise like an interrupt from every different type of device.
Okay.
Not like.
Yeah, I was saying looking for sequences, right?
Well, you just do all of the interrupts,
But pressing it, like again, pressing every key, unplugging my mouse, and pressing the power button
No,
all
but-
at once isn't gonna branch the same way, right?
But if you press an A or a D, I think it's the same interrupt. The MMIO access is what decides what key it is.
Okay.
So it will still know
So you're saying this is the redundancy of doing symbolic execution in MIO, right? And then we don't need to worry about this?
Yeah, like if you press an A, like it generates an interrupt, then it checks, okay, what key was pressed by reading MMIO. That's where the symbolic execution comes in. Maybe it finds some possible cases.
Okay, so this is handled already by what's in the paper, and we just need to raise the interrupt once.
Yeah, I mean, I have, for most of these devices, like different inputs are not going to produce different interrupts. It's the same interrupt.
Yeah.
Different, like the
Different
data.
values.
Yeah. Yes, other ideas? No, okay, so I guess we can wrap up here already over time.